Hello. We'll start the session in 5 minutes. Welcome to week number 9 of the live interactive session for traffic engineering. I'm Seri Vinayanam, a PhD scholar in the civil engineering department at IIT Madras. Okay, so let's begin with an overview of what was taught in week 9 for traffic engineering, and then we'll look at some example problems related to those concepts. Okay, so this week we were focused on two main concepts. One is car following models, and in the later part we looked at traffic simulation, traffic in particular micro simulation. So first we started with car following theory. Okay. So what is car following? So basically, uh, so car following is in car following models, what we are trying to replicate is the uh, driver's behavior when they are following other vehicles in the traffic stream, right? So when people are driving, so because of the presence of other vehicles sharing the same road space, there is interaction between these vehicles, and that affects the drivers the response, right? So different actions could occur, like acceleration, deceleration, cruising, or coming to a complete stop, right? So all these different decisions can be taken by the driver, like what speed to maintain, right? So whether to increase it or decrease it, what gap to maintain with the the leading vehicle. So all these decisions are dependent upon the driver behavior and also influenced by the traffic stream or the traffic conditions, right? So in car following model, what we are trying to do is trying to replicate these driver behaviors, right? So based on what we are observing in the field, right? So that's the objective or the goal of these car following models. So with respect to that, one of the terms that we need to be very clear about is the space headway, right? So because this is very important in the car following models. So what is space headway? So space headway, as we already know, is suppose we take two consecutive pair of vehicles on the road, right? So this is some vehicle I, this is followed by another vehicle, let's call it vehicle I plus one. Okay, so the clear distance, right? So the empty distance that is between the two vehicles on the road, the consecutive vehicles, this is the clear gap, right? But what space headway is you take two points on the corresponding points on the two vehicles. Okay, if we take the middle point of the ith vehicle, we have to take the middle point of the I plus one vehicle, right? And then the distance between those points, that is what we call as the spacing or the space headway. Okay, so typically, so we could take any two points, right? As long as they are, the same points on, the both the vehicles. But typically, what we do is take the front edge or the front bumper on the two vehicles, right? So from the front bumper of the first vehicle to the front bumper of the following vehicle, so we take that as our spacing. So because it is easier to observe in the field. Okay, so what does this comprise of? This comprises of the clear gap plus the length of the vehicle. Okay, so spacing has the clear gap as well as the length of one of the vehicles included in it, right? So that is our space headway. So why is this important? Is because this influences the decision, right? So as we can imagine, right? So if the vehicles are too close, the space headway will be smaller. So in that case, the follower vehicle, which is I plus one, will be very careful, right? So to the changes of the say the speed of vehicle I, right? So when they are very close and a vehicle I suddenly applies brake, so vehicle I plus one will also react to it quickly, right? Whereas if the gap is very large, even if vehicle I slows down, vehicle I plus one need not or may not slow down quickly or slow down too much, right? So the space headway is important because it influences the sensitivity of the driver's reaction is also dependent on it. So then we looked at different models in the from the literature. So the earliest ones being the pipes and the Forbes models of Forbes theories. Okay, so what does pipes theory say? So this was a simple model. So where the it was hypothesized that the clear gap or the minimum or the safe gap should be you know should increase by one vehicle length for every 10 meter per second increase in the speed of the vehicle. Okay, so what does this mean? So this is your safe gap. Okay, demon. So as we saw the spacing, safe spacing will contain the length of the vehicle plus the gap. Okay, so this is the length part. First term is the length part, second term is the gap part. And Pipe's theory was that as the speed increases, right, so for every okay, let me just zoom in. Is it better now? Okay. The Pipe's theory is the spacing should increase by the length of the vehicle for every 10 meter per second, or for every 10 units increase in the speed of the vehicle. Okay, so x dot, so x, we use x to represent the position of the vehicle, right? So x dot means it is the first derivative, right? So this is the speed, first derivative of position with respect to time. And x with two dots means the second derivative. So this is the change in speed. So that is the acceleration or the deceleration, right? So here, so for every 10 meters, increase in the speed, so the clear space, the safe spacing should increase by, one vehicle length, right? So vehicle length is represented by Ln. Okay, so that is the, pipes theory. So next one was the Forbes theory. So Forbes theory is, so Forbes tried to bring in the reaction time into the equation. Okay, so there he modeled the time headway instead of the space headway, right? So here we looked at space headway. So the related concept is the time headway. So what is time headway? The time headway is you take a point along the road. Okay, you take a location along the road, and then you calculate the time it takes for two vehicles to cross that point. Okay, so here we have vehicle I plus 1. Let us say this point P is crossed by vehicle I at time ti. Okay, and vehicle I plus 1 is crossing this time point P at time I plus 1. Then ti plus 1 minus ta, so that will be your time headway. Okay, so so what is the relationship between the space headway and time headway? So time headway is basically how long it takes for one vehicle to cross a point after another vehicle has crossed it, right? So if the vehicles are following each other closely, that is, and the space headway is small, so time headway will also and time headway will also be smaller, right? So because the vehicles are following each other closely, right? So if the space headway is large, right, so the time headway will also increase because the vehicles are far away, right? So it will also take a farther large time to also cover the same, to cross the same point as the leading vehicle. So here in Forbes theory, we are looking at the time headway. So the time headway is actually the summation of two components. One is the reaction time, right? So the reaction time is basically once the leading vehicle does some action, right? So like acceleration or deceleration, the following vehicle will take some time, right? So it cannot instantaneously react, right? So the driver will require some time to perceive the change and then react to that change. So that time taken is the reaction time, represented as delta t. Plus uh, So the Forbes is it also brings in the the relative the speed of the following vehicle, okay, and the time it takes to cover one vehicle length, okay. So that is the safe time headway as given by Forbes, okay. So this is the reaction time. This is the time taken to cover one vehicle length. Okay, so Ln is your vehicle length, x n plus x dot n plus 1 is the speed of the following vehicle. So how long it takes for the following vehicle to cover Ln distance, that is Ln by x n x dot n plus 1. Okay, so that time plus the reaction time. So that much should be the minimum time gap between the two vehicles, right? So for safe car following. So that's what was the theory hypothesized by Forbes. Okay, so what was found, these are very simple models, right? So we are only using the speed and the the vehicle length in these models, but despite their simplicity, what was found is the field measurements were closely replicated by these models, right? So especially in medium speed ranges, right? So when the speed was around 30 miles per hour, 40 miles per hour. So whatever was predicted by these models as the time headways or the space headways, those were very close to what was observed from the field. But when the speeds were either too low or too high, there were some deviations, right? So whatever these models predicted, were lesser. The field values were actually higher than what was predicted from these models. So that is one of the limitations. But despite that, this for such a simple model, so they did very well in replicating the field behavior. So in the second lecture, we looked at few more models. So these were developed by the General Motors company. So their group, research group, came up with multiple models. So actually five different models. So these are called first generation to the fifth generation models. So what the GM models had, so they had a particular theory like this. So they modeled the response of the following vehicle as a function of two things. One is sensitivity, second is stimuli or stimulus. Okay, so stimulus is the action from the lead vehicle, right? So this is some change that is happening. Okay, so this is the action by leading vehicle. Okay, so sensitivity is a characteristic of the driver, right? Driver or the follower, or how they perceive the stimulus. Okay, characteristic of the follower. So this is response also of the follower. Okay, so the leader causes make some changes. So to that change, the the follower responds. So what is that response? So this response is either acceleration or deceleration. Okay, and the stimulus that they use is the relative speed. So what is relative speed? The difference in the speeds of the leading vehicle and the following vehicle. Okay, so that is taken as the stimulus. So if there is a change in the relative speed, so depending on what that change is, whether if the relative speed is positive, right? So x leader speed minus x follower speed. Okay, so this is your relative speed, right? So if this is positive, what does this mean? The leader is traveling faster than the follower, right? So which means that if the follower didn't do anything, the gap between the leader and the follower is going to get bigger, right? So that gives the follower an opportunity to increase their speed, to travel at a higher speed, right? So there will be acceleration as the response. So if this is negative, so what does that mean? So the leader is slowing down, right? So the follower is traveling faster than the leader. So if this continues without any response from the follower, there could be collision, right? So because the follower is traveling faster, the gap is going to reduce. So the follower will respond by decelerating. So if this was 0, which means that there is no stimulus, the gap is maintaining, right? So they will continue, the follower will continue to drive at the same speed, right? So there won't be any acceleration or deceleration, right? So that's the basic concept in the GM models. So the first generation model, if you look at them, so acceleration or deceleration of the follower. So the notation that is used in the lectures is n is used to represent the leading vehicle and n plus 1 is used to represent the following vehicle. Okay. So the acceleration of the follower is equal to the product of the sensitivity, which is represented using alpha, times the stimulus. Stimulus is xn minus x dot n minus xn plus 1, right? So this is the difference in the leaders and the followers speed. Okay, so here on the left we are using the response is acceleration, right? So the unit is meter per second square, and the relative speed has the dimension of speed, right? So this is in the meter per second, right? So that's, which means that the dimension of the sensitivity should be 1 over second, right? So that the dimensions match on both sides, right? So that is the unit for the sensitivity in the first generation model. And then the second generation model, so what they observed is that the sensitivity was varying a lot, right? So depending on the spacing of the vehicles, right? So the drivers are not always equally sensitive to smaller gaps and larger gaps. So as we saw in the start, so when the gap is too small, the drivers will be very attentive and more reactive, right? So to small changes in the speeds of the leader. But when they are following at a larger distance, so in that case, small changes in the leader's behavior will not impact as much as it did when the gap is smaller, right? So the sensitivity changes with respect to spacing. So to account for that, so they brought in different sensitivity coefficients, right? So they had alpha 1, right? So when the spacing is small, or alpha 2, which is a different coefficient that is applicable for large spacing. Okay, so depending on the model trying to predict for small spacings or large spacings, right? So the sensitivity was varied, right? So that was the second generation model. But again, the limitation is that, so this is again still very limited, right? So we are just going with two constants, right? So the third generation model generalized this further, so where the spacing was directly incorporated into the sensitivity. Okay, so there it was alpha naught by the spacing. Spacing is what? The difference in the positions, right? So the position of the leader minus the position of the follower. So this is your spacing. So that was brought into the sensitivity term, and then the stimulus, it remains the same. Okay, so now the sensitivity part, this part, it is a function of the spacing itself, right? So what happens when the spacing increases, right? The denominator will become large and the sensitivity term as a whole will be smaller, right? So alpha naught is still a constant, so alpha naught by spacing will become smaller when the spacing becomes large, right? So sensitivity reduces, and when the spacing becomes small, right, so alpha naught by the smaller spacing will be a large value, right? So the sensitivity increases when the gaps reduce, right? So that's the third generation model. So here the dimension of alpha naught, the constant, is different. Why? Because so this is still meter per second square, this is meter per second, so spacing unit is meters, right? So alpha naught must have the unit of velocity, so that we'll have 1 over second as the dimension for this whole sensitivity term, right? So the unit of alpha naught is meter per second in the third generation model, whereas it is 1 over second in the first and the second generation models. And then in the fourth generation model, what they further expanded this. So in this, they found that spacing alone is not enough. to capture the sensitivity perfectly. So they plot the speed at which the follower is traveling, right? So along with spacing, if you are traveling at a higher speed, again you will be more attentive, right? Whereas if you are traveling at a lower speed, you will be less attentive to the less reactive to the changes. So in this case, the speed of the follower was brought in into the sensitivity term. Okay, so x dot n plus 1 divided by spacing is still present. Right, so this is the new sensitivity term, and then the stimulus is the same, the relative speed. Okay, so this is your fourth generation model. So in this, what is the dimension of the alpha naught constant? It is a dimensionless constant, right? So because we already have the velocity term and the spacing term, so these two together will give you a dimension of 1/2. So which means alpha naught should be dimensionless, so that you get the right dimension for the response. Okay, so that is your fourth generation model. And finally, the fifth generation model was a generalized model, right? So it brought in two power or the exponents. So one was the exponent for this speed, okay, and the other was an exponent for the spacing. So m and l and the stimulus. Okay. So depending on the value of m and l that you choose, you can have different models. Okay. For example, if you choose m is 0 and L is 1, what you will get is the fourth generation, the third generation model, right? So this will give you the third generation model where only the spacing is there in the sensitivity, and the velocity of the follower is not there. Okay. Whereas if you take both equal to 1, m is equal to 0, m is equal to 1, L is equal to 1, you will get the fourth generation model, right? So like this, you can have different models from the fifth generation model, right? So therefore, the fifth generation is a generalized model, generalized car following model. So that's what was covered in the second lecture. And in the third lecture, we looked at some example problem using the GM models. And then we also saw how the microscopic and the macroscopic models are related when using the GM model. Okay. So what is a macroscopic model? So these car following models are microscopic because we are looking at the behavior of individual vehicles, right? So we are looking at two particular vehicles in this particular car following model, which is a microscopic way of analyzing the traffic, right? Whereas in a macroscopic model, so what we are interested in is the traffic stream as a whole. So in which case we will not be looking at the relative speed or the spacing between individual vehicles. We'll be looking at parameters like the flow, density, right, or the speed of the traffic stream itself, right? So we are trying to look at the traffic stream as a whole in the macroscopic ones, whereas in microscopic we are concerned about individual vehicles or pairs of vehicles. Okay, so what they found is this third generation model. So it can actually be related to the Greenberg's model, right? So Greenberg's model. So we have speed is equal to some mu naught into kj by k, right? So we have the macroscopic model, right? So this was the Greenberg's model. So this Greenberg's model can be derived from the microscopic, General Motors model, right? So which means there is a relationship that exists between the microscopic aspect and the macroscopic aspect. So this was discovered, when these models were developed. Okay, so that was established in the third lecture. Then in the final lecture for car following, so we looked at traffic stability and other car following models like the Weidman models. So traffic stability is basically, how the response, whether the response keeps changing or over time, or it has a stable value over time, right? So we are looking at changes in the responses, right? So over time, so that's where we look at traffic stability. So here we have two different concepts. One is local stability and the other one is asymptotic. So in local stability, again, we look at only a pair of vehicles. Okay. So how is the response profile of the follower changing, over time, right? So for example, if you have a response like this, here you have time. Let's say we have the acceleration or the deceleration of the follower. Okay. And suppose it goes like this. So what is happening here? Here, the vehicle accelerates, then again it decelerates, again it quickly accelerates, again it decelerates, right? So which means that its response is continuously changing, also very quickly over time, right? So it's not very stable, with respect to time, right? So that means it is an unstable behavior, right? So or an oscillating behavior, right? So whereas if you have an acceleration, and then there is no acceleration, and then decelerates, so which means that it is stable over certain periods of time, right? So whenever there is a change, so it responds to the change, but then it is not changing too quickly, right? So there is periods of stability in that profile or in the response. So there, so for this traffic stability, so we measure it, as a product of two things. One is the sensitivity. So the alpha term that we had, so that um, you know that contributes to the stability. So the sensitivity of the follower, contributes to the whether the response is going to be stable or unstable. So the other part of the stability is the reaction time. So how quickly or how long it takes for the driver to react to the situation, right? So the sensitivity and the reaction times are two important components that relate to the traffic stability. So which means that if you have low reaction times and low sensitivity, so you'll have a very stable traffic condition, right? So when the C value is small, you have higher stability. When the C value is high, you have lower stability, right? So when the sensitivity is low and the reaction times are low, which means that you are not going to find this kind of oscillating pattern, right? So this is happening because the sensitivity is high, right? So because the changes are large, and also the reaction time is high, right? So quickly the changes are happening, right? So that's what we looked at in the stability concept. So local stability is considering only a pair of vehicles. Asymptotic stability, you extend this to a group of vehicles, right? So you take a line or a stream of vehicles, right? And then you look at what happens to the stream of vehicles as one vehicle changes its behavior, right? So that is the asymptotic stability. And then we have Weidmann's model. So again, similar to the other R models, here also we are trying to model the car following behavior, right? But here the Weidmann model defines different regions or states in which the car following can happen. Okay, so these include free driving, approaching, following, and braking. So these four regions or four states of car following are defined in this Friedman car following model. So free driving means when the drivers are not influenced by their surrounding traffic, right? So which means this is like the free flow condition, right? So the volume of traffic is lower, right? So the vehicles are far away from each other, so they can travel at their desired speed without being influenced by their surrounding vehicles, right? So they will be cruising at their desired speed. So that is the free driving region. So next we have the approaching region. So this is, so when you have a vehicle in front of you, okay, so that is traveling at a slower speed than you. So what do you do in that case? As you are going closer to the leading vehicle, so you will be slowing down, right? So to match the speed of the leading vehicle, right? So you are traveling at a higher speed, leading vehicle is traveling at lower speed. So as you are approaching that, you will be decelerating slowly, to maintain a safe gap, and then you will be traveling, right? So that is the approaching phase, the deceleration part. So that period is modeled in the approaching model as this approaching region. And then third, you have the following region. So this is once you have decelerated, and achieved the same speed or achieved the safe gap, right? So after that you will be maintaining that, right? So as long as the leader doesn't change their speed, so you will be maintaining that same speed and the same gap, right? And then follow that vehicle. So this is the following phase. And finally we have the braking phase. So this is when the vehicle has completely stopped, or say you have reached a traffic signal which has turned red. So in this case you have to come to a complete stop. So that is the braking phase. So here you will do a large deceleration, right? So compared to approaching, where there was a steady small or medium amount of deceleration, whereas in braking there will be a large deceleration which will bring you to a complete stop. So these are the four regions in which a vehicle can be present at any stage, right? So these four regions are modeled in the Wiedemann Karpalin model. And again, there are two variants: the 74 model, which is applicable for traveling on arterial roads, and then the Wiedemann 99 model, which is applicable for driving on the freeway. And then we moved into traffic simulation. Okay, so traffic simulation, what do we do? So why are we interested in traffic simulation? Is because so we are trying to model the traffic system, right? So the system consists of the physical infrastructure, right? So the roadways, the bridges, the traffic signals, intersection. So and then there are the users who are using the system, right? So the vehicles, the passengers, the drivers, the pedestrians, right? So who are using the infrastructure. So the interaction and the collection of all these entities together is what we call as the traffic system, right? So we are trying to model how this system works, right? So we are trying to replicate the reality through a computer program. So that's the simulation. But why are we doing that? Is because we want to make some changes to the system, and then study what happens, what is the result of it, right? For example, say there is congestion in the city, right? And we want to build a flyover, right? Or we want to widen the road, right? So what is going to be the effect of it, right? So we can, one thing that we can do is actually do or implement it in the field and then see what happens, right? But that is a very costly approach, right? So before knowing whether that's going to help us or not, spending huge amounts of money, and then finding out that it is not giving us the benefits, is a huge problem, right? So because it involves a lot of money and also physical disruptions to the existing traffic system, right? So therefore what we do, we replicate the behavior in a computer program, right? And then make the changes in the computer program, right? And then see what the reaction is in or the responses, and then determine whether that is a feasible approach or a beneficial approach or not, right? So we are trying to do a non-intrusive way of studying the system. Okay, so for this, so we have to correctly represent the system, right? So that's where we develop these different models. So the model is nothing but a replication of your the physical system, right? So and then we have different types of simulations. So like deterministic and stochastic. So deterministic means, like, if this is the situation, this is going to be the response, right? So if the situation is A, the response is going to be, and this is not going to change anytime. So whenever the input is going to be A, the output is going to be, right? So there is no randomness, right? So in that case, we'll call it as a deterministic way of simulating it. So on the other hand, if it is a stochastic simulation, which means there is a probability of getting different outputs for the same input, right? If the input is A, sometimes you can get B, sometimes you can get a response C, sometimes you can get a response D, right? And there is some probability associated with each of them, right? It's not going to follow any particular pattern. Say 50% of the time you can get B, another 30% of the time you can get C, 20% of the time you can get C, right? So like this, so if that is the case, so then we have a stochastic model, and then we can have static systems and dynamic systems. So static means, the static and dynamic is with respect to time, right? So if the system is not going to change over time, so in that case we go for a static simulation model, right? So if the volume is not going to change with respect to time, then it is a static volume. if there is change in the volume over day, so which is more realistic, right? So in the day, morning time and the evening time, during the peak periods we'll have a higher traffic, and in the off peak periods we'll have lower traffic, right? So which means that there is a change in the volume with respect to time of day, right? So those cases are modeled using a dynamic simulation model. And then we have one other classification, which is discrete versus continuous. So discrete means that the system will remain in the same state over a period of time, and then at different points in time there will be a sudden change in the system. For example, when you have traffic signals, right? So for a period of time, right, so 0 to, let us say t1. So let us say the traffic signal is staying red. So from over this period of t1 time, the flow is going to be 0, right? So at the number of vehicles that are going to cross the intersection, right, for that particular approach which you are modeling, it's going to be 0, right? There's not going to be any change because the signal is red. And once the signal turns green, suddenly the volumes will start increasing, right? So which means that this is a discrete simulation that we can apply here, because at different points in time, so you'll have sudden changes in the system, and within that period, the state is going to remain constant. Okay, so such simulations are called as discrete event simulations, and opposite of that is the continuous simulation, so where there will be changes at every point in time, right? So there can be changes at every point in time, so we have to model for every time step in the simulation program. Yeah, so those are the different classifications that we had. And yeah, so and then the principle for traffic flow modeling is, so what is it? It's basically, so you have to model how you are going to replicate the 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 reality or the ground truth, right? So how are you going to model the flows, right? So that is generally used. What we use is the the fluid flow, right? So we take the vehicle or the traffic stream to be flowing through the roads, following like a fluid flowing in a pipe, right? So we take those principles and then apply it to the traffic flow, and then see how the vehicle motion works. So that is in the macroscopic scale. But is in the microscopic scale, as we saw in the different models earlier. So we try to model the response of the individual vehicles, corresponding to their local surrounding. So that is that is called as micro simulation. And between these two, at the macro scale and the micro scale, we have the third level, which is the mesoscopic scale, where instead of considering an individual vehicle or considering all the vehicles together, so we are going to consider certain groups of vehicles, right? So these are called the platoons, right? So vehicles that are traveling in groups together, right? So those will be modeled as one entity. So that is the intermediate or the mesoscopic scale. So these are the different principles that we adopt. So and what we choose for our study depends on what is of interest to us, right? So if our interest is to look at system level changes, so then we need not look at each individual vehicle, and then look at macroscopic scale, what happens to traffic flow for different lanes, right? Which lanes are congested or not congested. So we do not have to look at acceleration deceleration profiles of individual vehicle, right? So like that, so depending on our application or intention, so we go for different, we choose the principle of traffic flow modeling accordingly. And then in the final two lectures, we were more focused on micro simulation, right? So what is micro simulation? As we saw, it is modeling the individual vehicles or individual paths of vehicles, right? So here we looked at what are the different inputs that are required, right? So you need the information on the supply. The supply, this means that you have to give the network information. What are the links? What are the intersections? So where signals are present, right? And then you have to give operational information. So which is like, suppose you have a signal. So what are the signal timing plans, right? So how the signal is going to operate, and whether, even if it is not a signalized intersection, like sometimes you can have right turns, permitted. Sometimes, right turn will be completely removed. So sometimes you have one-way operation, two-way operation of streets. right? So all these decisions, these are operational decisions, so that has to be pre-specified, right? So these are within the control of the engineer or the traffic planner, right? So we can change it as per our decision. So the other aspect is the demand aspect. So this is how many vehicles or how many people are wanting to use the system, right? So this can be supplied in terms of OD matrix, like from one zone to another zone, how many people want to travel. So again, this OD matrix can be a static one or it can be dynamic, right? So static means at any time of the day, this the demand is going to remain the same. Dynamic means for different times, right? So different number of people will want to move between the different traffic zones. Or we can give in terms of link volumes, right? So in this particular stretch of the road, this is the flow that is going to come in, right? So here we do not know where they are starting and where they are ending, but all we know is in this particular, they will go through this particular road, all right? So at this rate, right? So that is the link volume. So we could give the inputs in this form. So this is the demand side. So this is generally not in our control, right? So this is depending on the people, right? So this will come in from surveys, or field measurements. Okay, so those are the information that we give, and then so the model then takes these inputs, simulates the behavior, and then we will get the outputs. So the outputs again could be different things. So it could be so what is the say delays, and if it is an intersection that we are analyzing, again what is the link flows. So if we give the input as an OD matrix, so we can find out what is the link flow that is happening, which routes people are choosing, and then what is the flow that is happening on different links, like that. So again, what is the density, so what is the speed that is experienced. So all these different metrics can be derived as an output of the simulation model. Yeah, and then how do we analyze these outputs? So so when it comes to analysis, so we look at whether these models are replicating the reality. So you will have some ground truth. So you take the inputs, as well as you can measure these different quantities from the field, right? So and then you compare the output that you have got from the model, compare it with the output that you have observed from the field, right? So and then see if they are matching. So that is one way you could do it. Other way is to look at statistical analysis, right? So you look at multiple runs of these simulation models, and then see the distribution of the outputs that are coming. Compare that with the distribution, hypothesized distributions, or the empirical distributions, and then see for the statistical significance of these results. And then performance measure. Again, you could have compare, as I said, what is the RMSE, MAE, right? So you have different measures to compare these values, right? So compare the stream density or the stream flow from the model with the the field values, and see how close these are in terms of these, right? So those are the different ways in which we can evaluate the traffic simulation models. Okay, so that's all that was covered in week 9. Okay, so let's move into the problems for this week. So the first problem is the leading and the following vehicles travel at a speed of 16 meters per second and have a space headway of 25 meters. At time t equal to 0 seconds, the lead vehicle accelerates by 1.2 meters per second square for 1 second. The simulated behavior, which is acceleration, speed, and position of the following vehicle, uses the General Motors first car following model, and it's shown in the table below. Okay, so we have this table, right? So where we have x1 is the leader. Okay, the 1 is for the leader, 2 is for the follower. So we have acceleration, we have speed, and then we have position, right? So this is given for the leader as well as the follower. And then we have the relative speed, and then we have the spacing, okay, for different time steps. And this x means those values are unknown, we need to fill that. Okay, So this is the General Motors first car following model, right? So in first generation model, we model the acceleration response as a function of the relative speed and sensitivity constant, okay, alpha. So here we assume that the sensitivity coefficient alpha is 0.5 second inverse and the reaction time delta t is 1 second, okay, and we update the model every zero point 0.5 seconds. The question is, we want to find what is the speed of the lead vehicle at t equal to 2 seconds and what is the distance headway in meters between the lead vehicle and the following vehicle at t equal to 2 seconds. What is the value of acceleration for the following vehicle at t equal to 2 seconds and what is the speed of the following vehicle at time t equal to 2 seconds. Okay, so these are the different things that we want to calculate. Let me just zoom in to this table. Okay, yeah. So maybe you can take 2-3 minutes and then we can see the answer. So the model is, so this is the GM model. So the circled cells are to be filled in. Okay, so those are the four values that we want to find. Yeah, the numbers given are the actual values. So the x are unknown values. Okay, so we want to find the unknown values. We want to find the x values. So all these, so these are unknown. The numbers that are given are correct, right? So those cells are correct. So the x marked cells are actually unknown cells. Yeah. If you have any doubt, you can ask. So are you clear with what you have to do? Yeah, so the values that are given, for example, at time 0, so the leader's acceleration is 1.2 meter per second square. Velocity is 16. It is at a position of 25. So these values are given, right? So these are known values, right? So for example, at time equal to 1 second, so we know the leader's acceleration is 0, but we do not know what was the speed of the leader at that time, right? So we need to find out what the speed will be at time 1. So given the information, like the speed was 16.6 at time 0.5 and the acceleration was 1.2 meter per second at that time. So what is going to be the speed of the leader at time equal to 1 second, right? So like that we have to find out all these x values. So given the values that are present, right? So with those known values, we have to find out what those unknown values are at different time steps. So you have to calculate the values in the cells marked with X. So I have to use the General Motors first generation model for the follower. For the leader, you don't need that. Let me just give you one example. Right. So for example, if you want to find the speed of the leader, say at time t equal to 1 second. Okay, so that is this particular cell. Okay, so how do you do that? So that is see. So that is so the what is the speed at time equal to 1 second is going to depend on whether the vehicle accelerated or not in the previous time step, right? So what happened at t equal to zero point 0.5 is going to influence what is going to be the value at t equal to 1. Okay, so this is nothing but uh, the acceleration at the previous time step, right, multiplied by the time step, okay, plus whatever was the speed at the time step. Okay, so what is acceleration? Acceleration is the change in the speed, right? So you have the previous time step speed plus the change in that previous time step speed, right? So the change is given by the acceleration multiplied by the time duration, right? So what was the acceleration? It was 1.2 meter per second squared multiplied by our update time interval is half a second, right? So zero point 0.5 plus what was the speed at time equal to zero point 0.5, it is 16.6 meter per second. Okay, which means that the new speed at time equal to 1 is going to be zero point 0.6 plus 16.6 is going to be 17.2 meter per second, right? So this is the speed of the the leader, right, at time equal to 1 second, because it accelerated at a rate of 1.2 meter per second for half a second from zero point 0.5 to 1. right? In half a second, it accelerated at a rate of 1.2 meter per second square. So the speed will be 17.2 meter per second at time equal to 1. So like that's like that we have to fill all the cells, right? So this is for the speed. For position, you have to use the equation of motion, right? So like the position is ut plus half a t squared, right? So here you will use the previous time steps, velocity as well as the acceleration, right? And t will be again the delta t that we use, right? The update time step. So using that, you can fill in the position column. So like that, you have to do and fill the other cells. Okay, any answers so far? Shall we look at the solution then? Okay, so these are the solution given here for the four parts. Okay, let's see how to get those. Okay, so as I said, see first, this is your leader up to here. This is the leader's position, velocity, and the acceleration. And this is for your follower, and then we have the relative speed and the spacing. Okay, so for leader, so you don't need to look at the follower values, right? So leader's speed or the position is not influenced by the follower, right? So follower is behind, so he's not going to influence. So the velocity of the leader is going to depend on the acceleration at the previous time step, as I said earlier. So here he's accelerating at a rate of 1.2 for half a second from zero point 0.5 to 1. So which means that the change is going to be 0.6 meter per second. Okay, so it's going to add up. So 17.2 is the new velocity. Okay, so x dot 1 at time equal to 1 is equal to x dot 1 at time equal to zero point 0.5 into zero point 0.5 plus x dot 1 at time equal to 0.5. So this was 1.2 times zero point 0.5 plus 16.6, which is equal to 17.2. Okay, now what happens? The vehicle stopped accelerating from time equal to 1 seconds, right? So that's why it is 0. The acceleration is 0 for the remaining time steps. So which means that acceleration is 0 means the change in velocity is 0. So which means the velocity is going to remain constant. So there's there's not going to be any further change. So it's going to remain at 17.2 only, right? So if you plug it into this equation, so you can see that the first term will always be 0, right? So because acceleration is 0, so which means whatever was the speed at the previous time step, so that will be the speed at the current time step as well, right? So because it is 0 here, so this will be 17.2, it is 0 there. So the next time step at time equal to 2 also, it will be 17.2, right? So the first question asks, what is the speed of the leader at time equal to 2 seconds, right? So this is the speed of the leader at time equal to 2 seconds. So that's why we have 17.2 as the answer for the first part. Okay. So next, we finished the speed of the leader. Next, we can look at the position of the leader. Okay. So for position, what will we do is position will be the speed at the previous time step. Speed into time plus half a t squared. Okay, this is nothing but ut plus half a t squared. Okay, so now first for finding the position at time equal to 1.5. Okay, so that will be x1 at 1.5. So for that we have to use the speed at the previous time step, that is 17.2 into time step is zero point 0.5 plus half a t squared. So half into what was the acceleration? Acceleration was 0, right? So into 0.5 squared. So this term is going to become 0. So it is only 17.2 into 0.5. So this is the distance traveled in that half a second. Okay. So this has to be added to 41.6. Okay. So this is the, say, delta x1. Okay. So this is, so x1 at time 1.5 will be x1 at time is equal to 1 second plus the delta x1. So that was 41.6 plus 17.2 into, zero point 0.5. So that is 8.75 plus 41.6, so 50.35. Okay, so that is the position at time equal to 1.5. So similarly, we can repeat it and then find the position at time is equal to 2 seconds. Okay. So what will be the position at time equal to 2 seconds? Is the position at time is equal to 1.5, which is 50.35 plus speed is 17.2 into again 0.5. Acceleration is still 0. Okay. So it will be another 8.75 added to it. 59. Okay. So that is for the position of the leader. Okay. So we only need the leader's speed and acceleration to calculate it. So now coming to the follower. Okay. So first, so here we have a missing value in the acceleration. Okay. So but acceleration, so for the follower's acceleration, we have to use the car following model. Okay. So what was that? So that was w dot 2 at t plus delta t would be alpha into x dot 1 t minus x dot 2 at t. Okay. So it is the relative speed at the previous, or one reaction time earlier, right? So here we have to be careful of the reaction time and the update time, right? So update time is 0.5 seconds, right? So every 0.5 seconds we update all these values, right? But the reaction time is 1 second, okay? So for which means that the response at time equal to 2 seconds is going to depend upon whatever was the stimulus present at time equal to 1 second, right? So because the driver perceives the changes every 1 second only, right? So if a change had happened at 1.5, so that is not going to influence what happens at 2, right? So which means so the response at time equal to 2 seconds, it will be stimulus is 0.5, right? Sorry, the sensitivity is 0.5 that is given to us. So this is multiplied with the relative speed at time equal to 1 second. So relative speed at time equal to 1 second is 1.2 meters per second, right? So this is 0.5 into 1.2. So which means that it is 0.6 meter per second square. So that is the response, right? So that is the acceleration of the follower at time equal to 2 seconds. Okay. So this is coming from the car following model. So now we have the acceleration values. So with that we can repeat whatever we did for the leader to get the speed and the position. Okay. Yeah. So spacing is unknown, right? So spacing is directly we can get it because we know x1 and x2. So it is 41.6 minus 16 for the time step 1 So that is 25.6, right? That is the spacing at time step 1. So next we can calculate what is the velocity at time equal to 1. So because the acceleration is 0, right? So which means that is what is going to affect what happens at time step 1.5. So there is not going to be any change here. Okay, it is still going to be 16 meters per second. Now for time step equal to 2, right? So the acceleration, the vehicle has accelerated by zero point 0.3 meter per second square. Okay, which means that going to be 16.15, right? Or approximately 16.2, right? So because zero point 0.3 meter per second square change happens in 1 second, but we are updating every half a second. So in half a second the speed would have increased by 0.15 meter per second square, meter per second. So it is 16.15 or 16.2. Okay, so that is the follower's speed. And the position, yeah, position for the only one value is missing here. So position will be the previous time step speed is 16 into 0.5, that is our update time. Acceleration is 0.3, right? So half into acceleration 0.3 into 0.5 squared. Okay, we solve that. So this is 8.04. Okay, so which means it's going to be 32.04 is the new position for the follower. Okay, time equal to 2. So and then you can get the the relative speeds and the spaces. Okay, so the relative speed will be what, 16 and 17.2, which means that it is 1.2 again. Okay, and the difference in the spacing will be 50.35 minus 24, so that is 26.35. And for the last time step, the relative speed is 16.2 and 17.2, so it is like 1 meter per second. And the difference in the spacing will be, difference in the position will be 59.1 minus 32, that is 27.06. Okay, so we got all the values. Okay, so we fill the positions, we fill the speed, position, and the acceleration for the leader as well as the follower, right? So for the leader we don't need the car following model because the leader is not following, right? When we are considering this pair of vehicles. And for the follower we have to use the car following model to find out the acceleration response, right? And once we have the acceleration response, from that we can get the velocity as well as the position, right? So that's how we use this car following model to update our outputs. Okay, now moving on to question number 2. Here we have to accept or reject the given statement. The statement is, as per the third generation car following model, the dimension of alpha naught constant in the sensitivity term is meter per second square, right? So here, so the third generation car following model is alpha naught divided by x n minus x n plus 1. This is a time t. Okay, and this is the spacing. Okay, so the sensitivity has alpha naught, which is a constant, and divided by the spacing between the vehicles multiplied by the relative speed. Okay, so here the unit of the response is acceleration, so it is meter per second square. The unit of the stimulus, which is the relative speed, is meter per second, which means that the sensitivity term should have a unit of 1 over second, right? But we already have, second within the coming from the meters coming from the spacing term. Okay, so which means the alpha naught should have a unit of meter per second, right? So the overall dimension of the sensitivity term will become 1 over second. Okay, so that the response will have the correct dimension. Okay, so which means that this is not dimensionless. It is meter per second, so that we accept the given state. Okay, it is not meter per second square. It is meter. It should be, yeah. So it is meter per second. So okay, because it has to be meter per second, right? So it's given as meter per second square, so we are rejecting it. Okay, misread it. So we are rejecting it. So it was the incorrect dimension. The question number 3 is, which of the following statement is false with respect to space headway? The options are: space headway is inversely proportional to time headway. Traffic density is directly proportional to average space headway. C, larger the spacing between the vehicles, higher is the level of service. And D, space headway lower than critical spacing results in a very high level of service. Okay, so here we want to identify the false statement. Here, the first statement, space headway is inversely proportional to time headway. Uh, yeah, so that is correct. So when you have a larger space headway, you will have a larger time headway as well, right? So as the spacing increases, right? So the time taken for the corresponding point of the two vehicles to cross a given point will also be larger, right? So, and then the traffic density is directly proportional to the average space headway. So that is not correct. This is inversely proportional, right? So which means density is inversely proportional to the spacing, right? So we'll take density as like 1000 by the spacing given in meters. Okay, so that will give you the density as number of vehicles per kilometer per lane. Okay, which means as spacing increases, right, so your density will come down, right? So when the gaps are large, the number of vehicles in a given length of the road will come down, right? So therefore, that is incorrect. C is larger the spacing between the vehicles, higher is the level of service. So this is true. So when you have larger spacing, you have lesser density, right? So you'll also have higher speeds, right? So which means the level of service is going to be higher, right? So there won't be traffic congestion. And D is space headway lower than the critical spacing results in a very high LOS. This is also true. So critical spacing. So which means the density is smaller, right? So when the space headway is smaller, smaller than the critical spacing. So till the critical spacing, so you will have a very good LOS. Once the critical spacing is crossed, which means the density is going to be very high. So in that case, your speeds will come down, right? And congestion will be higher, right? So in that case, your LOS will be lower. So when the space headway is lesser than the critical spacing, the LOS will still be higher, right? So which means the statement B is incorrect out of the given ones. Okay, question number 4 is, accept or reject the statement. The underlying logic of traffic microsimulation models is inherently deterministic. Okay, so here, so we are talking about the microsimulation models. Yeah, so the underlying logic is not deterministic, so it is stochastic in the microsimulation model, right? Which means that we'll have a predefined distribution, okay, for the different parameters, right? So the parameters of the distribution will be calibrated in the model, right? So but they are not deterministic, right? So which means that each time some random draws from that distribution will be picked up, right? For example, in terms of volumes, what we generally give is, right, the volume in terms of vehicles per hour, that are coming to a particular intersection, right? So we do not say how many vehicles are going to go through or how many vehicles are going to turn right and turn left. So we do not specify it like that. So the number of vehicles that are going to go straight through, number of turning vehicles, those will be drawn from a pre-specified distribution, right? So according to that, the number of vehicles that are going to go through or turn, that will be determined, right? So which means that it is going to be changing every time, right? So it's not going to follow the same value. It will be a stochastic process. So like that, the different logics in the model will also be having their own distributions, right? So which will be calibrated for the different field settings, but it is not deterministic. So therefore, we reject the given statement. So question number 5 is, as per the General Motors car following model, if the lead vehicle decelerates at time t, the following vehicle at delta t will be dash accelerates, decelerates, or there won't be any change in the speed of the following vehicle. Okay. So here, so in the GM models, what we have the acceleration or the deceleration of the follower, right? So this is a function of the relative speed, right? So what happens if the relative speed is positive, right? So xn minus xn plus 1 is positive, right? So which means that the response will also be positive, right? So positive response here means acceleration of the follower, right? Because the response is the acceleration or the deceleration. So positive means it is an acceleration response. Okay. So if it is negative, the relative speed is negative, which means that the leader is slowing down. Okay, so the leader is traveling at a smaller speed, which means that the follower will decelerate. Right, so acceleration will be negative, which means it's a deceleration. And if it is zero, if the relative speed is zero, then the response will also be, the zero. Okay, so there won't be any change in the speed of the follower. Okay, so here in the question we are asking if the lead vehicle is decelerating. Okay, so which means it is, so these are the three cases. So lead vehicle is decelerating, which means that we are going to have a negative relative speed. Okay, so therefore the response will also be deceleration. So the right answer is option B. Okay. So question number 6 is, which of the following statements is true with respect to the Forbes car following theory? Option A is minimum safe distance headway decreases linearly with speed. Option B is the minimum safe time headway continuously decreases with speed. Option C is at lower and higher speeds there is considerable similarity in pattern to the pipes model. And D is H-min is the difference between the reaction time and the time required for the lead vehicle to traverse a distance equivalent to its length. Okay, so here these statements we have to look with respect to the Forbes model. Okay, so in Forbes model, what do we have? So we model the minimum safe time headway that is required. Okay, so that is given as the summation of the reaction time delta t and the time taken to cover one car length distance, at the follower's speed. Okay, okay, the follower is traveling at the speed x dot n plus 1. So then it takes ln, which is the length of the car. Okay, the ln divided by the speed, that is the time taken to cover one car length. So that added to the reaction time. So that is the minimum required, time headway, in the car following behavior. Okay, so that's the Forbes theory. Okay, so here option A says minimum safe distance headway decreases linearly with speed. Okay, so to save distance headway decreases linearly with speed. So what happens when speed is increasing? So given that the reaction time and the car length, so they are not going to change. The speed is going to increase. Okay. So what happens here? Time headway is going to decrease. Okay. Right. And what we know is that these two, time headway and the space headway, are inversely related. So which means that if time headway is going to go down, here required space headway, right, it has to increase, right? So which means it's not going to decrease with speed, right? It's going to increase with speed, right? So therefore, A is not the right one. B is minimum saved time headway continuously decreases with speed, right? So that is true, right? As your speed increases, it is going to linearly, the time headway is going to linearly decrease, right? As we saw earlier. So this is correct. And C says at lower and higher speeds, there is considerable similarity in a pattern similar to Pipe's model. So this is wrong because, so here we are looking at the similarity in pattern between the model's prediction and what is observed in the field, right? So whether the model is able to replicate the field observations. So actually what it is the opposite of this. At medium speed ranges, there is a good agreement with the field values. Medium speed, good agreement with field observation, right? But at lower and higher speed, there is considerable deviation, right? So, but C says otherwise, right? So actually, there is considerable similarity in the medium speed ranges, right? And there is a deviation at the lower and higher speed ranges. So C is incorrect. And D is H1 is the difference between the reaction time and the time required for the lead vehicle to traverse a distance equivalent to its length. So it is incorrect because it is not the difference but the summation of these two components, the reaction time and the time taken to travel one car length distance, right? So it's the sum of those two, not the difference. So D is also incorrect. So the right statement out of the four was option B. Okay, question 7. The statement given is model verification is the process of modifying the default microsimulation parameters so that the model replicates the observed traffic conditions as accurately as possible. Okay, so here, so we have verification, validation, and we also have calibration. And so these are different steps that we have in our model building or the model training process. So verification is basically, so you have defined some logic or some rules, right? So as part of your model, right? So for example, so to replicate the traffic signal behavior, so when it is a red signal, the vehicles cannot cross the intersection. When it is green, they are allowed to cross, right? So that is the rule or the logic that we have fed into the model, right? And then we look at as the model works, right? So we look at whether this logic is satisfied or not, right? So whether the model is following this logic or not, right? So for example, if the cars are crossing during the red signal, right, so instead of stopping, so which means that the model is violating the logic, right? So that's what we do in the verification process. We check whether the coded logic is respected by the model, right? So that's all we do in the verification. So the calibration is, so there are different parameters, as I said, so we'll have distribution with different parameters, or so the driver behavior, the sensitivity. So those are like, there are numerous parameters that we can change, right? So what we will do in the calibration process is, what set of parameter values will give us a close fit of the observed values, right? So if I change one particular parameter value, right, right, so for example the sensitivity, right, so then the different parameters, that different measures that I calculate, right? So for example, the deceleration profile, or the delays, right, so the other space headways that are maintained, so those will be changed, right? And then we see which set of values or which value will give me a close replication to what I see in the field, right? So and then we find try to find that set of parameters that gives me the best fit. Okay, so that is the calibration step. And then the validation is once we have a set of calibrated parameters, okay, we try to apply this set of parameters to another set of data, right? So we collect from the field, we'll collect two sets of data. Okay, so one is for calibration, another is for validation. And so these are two sets of data, maybe from the same place or they can be from the different locations with similar characteristics. Okay, so here from here what we do is calibrate the parameters of the model. Okay, parameters are found. Okay, and then what we do is take these found parameters and then apply it to the validation data, right? And then we see whether those calibrated set of parameters are able to explain what we are seeing in the validation data correctly, right? So if it is closely uh, explaining what we are seeing in the validation data as well, then we have a valid model, right? So it's not that these parameters work only for one set of data, but these are generic and then work for other data collected at other times maybe. So these are generic or valid parameters. Okay, so that's the validation process. So these are the three major steps that we have. So here we are talking about the verification step. So that says that it is a process of modifying the default parameters so that the model replicates the observed traffic condition as accurately as possible. So this is incorrect because this is what we do in the calibration step, right? So in calibration, we adjust the parameters so that we are matching closely with the field values, right? So this is the definition of the model calibration step, not the verification step. Therefore, the given statement is rejected. Then question number 8. Which of the following statements are incorrect with respect to General Motors car following theory? So the options are: as per the second generation model, a high sensitivity value alpha 1 should be employed when the vehicles are far apart. Option B is the third generation model takes into account the distance headway between the lead and the following vehicles. Option C is the fourth generation model is developed to improve the sensitivity term by introducing the speed of the leading vehicle. And option D is in a generalized car following model. If distance headway exponent is 1 and speed exponent is 0, it will result in the third generation CF model. Okay. So, second generation model. So, what is the second generation model? Second generation model had two sensitivity parameters, right? Alpha 1, alpha 2. So, one of these two will be used, okay, depending on whether the spacing is small or large, okay, and this is multiplied with uh, the relative speed, okay. So we'll have a high sensitivity value when the spacing is small, right? So because when the vehicles are close to each other, right, so the sensitivity will be very high, right? So the drivers will respond with the high acceleration or deceleration. And then if the spacing is is high when the vehicles are far apart, the sensitivity to the stimulus will be lower, right? So that's why we have two different sensitivity parameters in the second generation model. And so the statement says a high sensitivity value is used when the vehicles are far apart. So that is incorrect. So high sensitivity is used when the spacing is small, okay? But when the spacing is high, the low sensitivity value will be used. Therefore, A is incorrect. B is third generation model takes into account distance headway between the lead and the following vehicles, and that is correct. So because there is change in the sensitivity depending on the spacing, so that was explicitly brought in the third generation model instead of having different constants, right? So the spacing was brought in as a term in the third generation model where we had alpha 0 by the divided by the spacing xn minus xn plus 1. So this is your new sensitivity term multiplied by the relative speed. So which means the distance headway or the space headway is accounted for directly in the third generation model. So B is correct statement. C's fourth generation model is developed by improving the sensitivity term by introducing the speed of the leading vehicle. So this is also correct. So fourth generation model added one more term. So alpha 0 by the spacing, so is multiplied by the speed of the, okay, so this is actually incorrect. So it's not the speed of the leading vehicle, it is the speed of the following vehicle, right? X dot n plus 1. So the speed at which the follower is traveling is going to influence their sensitivity, okay? And then the stimulus is still the relative speed, okay? So if someone is traveling at a very high speed, right? So they are going to have a higher stimulus, right? So they are going to be very attentive, right? So because it's more riskier, right? So therefore you will be very cautious when you're traveling at a higher speed and then respond to changes, right? So you will respond with larger or higher changes, okay? Therefore, the speed of the follower is important, okay? So that was incorporated. It's not the speed of the leading vehicle, so therefore C is also incorrect. D is, in a generalized car following model, if the distance at V exponent is 1 and the speed exponent is 0, it will result in the third generation model, okay? So the fifth generation model had, the speed of the follower had an exponent, right? So power of m, and the spacing also had another exponent, okay? It's called L, and then the stimulus. Okay, so here we are taking the distance set by exponent, so this L term, so that is 1, and this m term is 0, okay? So speed exponent is 0. So speed exponent is 0, which means that the speed term is not there in the model, okay? So it reduces to alpha 0 by the spacing into the relative speed. So this is exactly the same as your third generation model, right? So only the spacing is there in the sensitivity, the speed of the follower is not there, right? So therefore, when for this combination of the exponents, okay, so it will become the third generation model, okay? So because the fifth generation is a generalized model, right? So for different combinations of the exponent values, so we can get the different models that we already have, okay, and some other models as well. So therefore, out of the four, only options A and C are incorrect. Question number 9 is, in traffic microsimulation, traffic demand is typically entered as individual vehicle movements rather than as deterministic number in vehicles per hour. Okay, so here, so this is an incorrect statement. We reject it, right? As we already discussed. So we will give the input in terms of for example, the link volumes, right? So this many number of vehicles are going to use this link, okay? We do not say how many vehicles are going to turn right, turn left, like that, right? So that is modeled as a stochastic process, right? So we take it from a distribution, right? So we observe from the field, right? So as the turning the different movements follow a particular distribution, and then from that distribution we try to sample each time and then use that for the simulation, right? So therefore we do not specify individual movements, okay, like how many straight through, how many right, how many left. Instead we just say this is the total, the inflow that is going to come in, right? So from that, so these three movements will be sampled from a distribution and then used, and then the different movements will be modeled, okay? So therefore the given statement is incorrect. Question number 10 is, which of the following statements are correct with respect to stable behavior in the car following theory? Option A, over response. Option B is high reaction times. Option C is low sensitivity, and option D is attentive time. Okay. So here, so a stable behavior means the C value has to be lower. Okay. So what is the C value? It is the product of your sensitivity and the reaction time. Okay. So if this has to be lower, so these two has to be lower. So low sensitivity, right, and low reaction times will give you a stable car following behavior, right? So which means that, so option C, right? So the sensitivity should be low and the reaction time has to be lower. So reaction time is lower means the driver is attentive, right? So the driver is keenly following the leader's movements, right? So, and then any change results in a quick, response from the following driver, right? So, which means the driver has to be attentive, right? So, in that case, you'll have a lower reaction time, and when you're able to quickly respond, right? So you have, which means that you have enough time, enough time headway or enough space headway available to you, which means that you don't have to respond with higher values of acceleration or deceleration because you are reacting quickly. So you have enough time, so you can slowly accelerate or decelerate, right? So therefore the sensitivity will also be lower. So these two combination will give you a stable traffic condition, right? So on the other hand, over responses, when you have a higher sensitivity coming from a higher reaction time. So when you have a higher reaction time, which means you are reacting slowly. So by the time you are able to make an action, right? So your space or the time headways have gone too low, right? So therefore you have to respond with a higher acceleration or deceleration, right? So because you have gone too close, right? Or you have gone away too far, right? So the gap has been higher, so you will be accelerating too high. Okay, so that it will result in over response or a higher reaction time. So that is for unstable conditions. So for stable condition, only options C and D apply. Okay, then question number 11 is with respect to the traffic stability, the value of C equal to 0.6 indicates that no oscillation would occur between the lead and the following vehicle. There would be increasing oscillation between lead and following vehicle. None of the vehicles will collide considering a line of following vehicles, and two or more of the following vehicles may eventually collide considering a line of following vehicles. Right. So for here, so there are two kinds of traffic stability that we will look at. One is local stability, which is applicable for which is discussed in options A and B. So in local stability, we are looking at only the lead and the following vehicle. Okay, only a pair of vehicles. And the second type is asymptotic stability. Right, so where we look at a line of vehicles. Okay, so there is a leader, and then there are a line of vehicles following this leader. So the stability of this whole line of vehicles is what we call as the asymptotic stability. Okay, and so for local stability, we have three groups or three ranges of values. Right, so if C is less than, I think it is 0.37. Yeah. So if the C value is between or is less than 0.37, okay, you have a no oscillation in the response, or this is a stable condition. Okay, and then when you have C greater than 0.37, but it is less than 1.57, okay, this this is called as damped oscillation. Okay, which means that it is not stable, right? But over time it will become stable, right? So which means there will be some oscillations present, okay, but these oscillations will die, and then the vehicle will get into a stable condition over time. Okay, so that is in this range. And then when this exceeds and C is greater than 1.57, what we have is an increased oscillation. Okay, so increased oscillation means, so it will so the traffic is in an unstable condition, okay, and then it is going to, these oscillations in the response is going to become larger and larger with time. Okay, so those are the three regions of this traffic stability for when we are considering local stability. Okay, so here a value of 0.6 in this case, which means that it is in the damped oscillation state, right? So it is between 0.37 and 1.57. So the oscillations will be present, but it will not increase with time. So which means option A is also incorrect because it says there is no oscillation. That is not the case. There will be some oscillation. And B says the oscillations will keep on increasing with time. Okay, so that is also not correct because this is damped oscillation. It will not increase, but it will reduce with time. Okay. So both options A and B are incorrect. So for C and D, we have to consider the asymptotic uh, traffic stability. So in asymptotic case, we have only two regions, right? C, if it is less than 0.5, it is stable, and if it is greater than 0.5, it is unstable. Okay, only two states, okay, two regions, okay. So in this case, we have zero point 0.6. So zero point 0.6 is greater than 0.5, which means that there will be unstable asymptotic. The asymptotic stability is unstable, okay. So which means, what does that mean is that, so some vehicle in the line of vehicles that we are considering, there will be some collisions happening, okay. Right, so it could be two vehicles, or it could be a string of vehicles, right? So more than two of them, so they may come into collision, okay. So that's what the instability in the asymptotic case mean, which means option D is correct and C is incorrect. So C happens only in the stable condition, okay. So where there won't be any collisions, but in the unstable condition, so some vehicles will collide eventually, okay. So therefore the correct answer is option D, okay, out of all the four. Then question number 12. Here we are given different, driving states. So this is from the Weidman model. We have free driving, approaching, following, and braking. And then we have the descriptions corresponding to those driving regions. So we have to match them correctly. Okay, so first is, free driving. So free driving means, so there is no influence of the surrounding vehicles, and the driver is able to travel at their desired speed, right? So there is no influence of the leader or the surrounding environment. So therefore, that is the free driving case. Like, it is like traveling at a free flow regime. Okay, so which means the driver is able to maintain his desired speed. So second is approaching. Approaching means the driver is approaching a vehicle, like a leader vehicle, who's traveling at a lower speed, right? So therefore, the driver has to slow down so that they are able to maintain a safe gap, right? So therefore, in approaching, the driver adapts to a lower speed of the preceding vehicle, okay. And then following means, so once the driver has lowered the speed when they are approaching, so they have now lowered the speed, they are having a safe gap, right? And now once that is achieved, they will try to keep this distance or the safe gap as a constant, right? So they won't let it increase or decrease, and try to keep it at a constant speed, constant gap, right? So that is the following region. So that is given in C. Okay, driver keep the same distance. And finally, we have the braking regime. So in braking regime, the driver will, apply high deceleration rates, and then try to, the car may even go to a stop condition. Okay, so that is the braking condition. Okay, there is a quick, reduction in the speed. So those are the correct descriptions. Okay, so that is 1D, 1B, 2D. Okay, that is here 1B, 2D, 3C, and 4A. So the right option is option D. Question 13 is, the statement is, the state of the traffic signal indication indicates a discrete model. Okay, so this is a correct statement, right? So we saw in the classification of simulations, so discrete simulation and continuous simulation. So in discrete simulation, for given periods of time, there won't be any change in the state of the model. Okay, so which means all the conditions, all the variables, they are not going to change for certain periods of time, right? So that is in the discrete model. So the traffic signal can be simulated as a discrete model, because for a given period, right? So when the traffic indication is a particular value, right? So when it is a red, there is not going to be any movement. When it is green, the vehicles are going to move. So in that period, the behavior is going to, or the state is going to be in a particular value, right? So therefore, signal is a example of a discrete model. Okay, therefore we accept this given state. Question number 14. Yes, we have some traffic flow modeling principles and their corresponding descriptions given in this table. Okay, so the three modeling principles are macroscopic, microscopic, and mesoscopic. And the descriptions are individual vehicles. Vehicles are packed in platoons, aggregated point of view. So here the macroscopic means we are looking at like the bird's eye view, right? So we are looking at the system as a whole, right? So which means it is an aggregated view, aggregated point view. Okay, so we are considering the traffic stream and not looking at individual vehicles in this macroscopic approach. Then we have the microscopic approach, which is the other extreme, right? So instead of looking at all the vehicles together, we're going to look at individual vehicles and their responses, right? So like in the car following model, so we are going to look at how each vehicle is going to respond. So that is the microscopic, right? These are the two extreme approaches. And then finally, we have mesoscopic, which is a compromise between these two, right? It's not looking at the aggregated all the vehicles. It's not looking at individual vehicles. Instead, it's going to look at platoons of vehicles, right? So vehicles, traveling together as a group, right? So that is the platoon. So mesoscopic scale, it is intermediate between the microscopic and mesoscopic, microscopic and macroscopic. Okay, so which means the right match is 1C, 2A, and 3B. So that is given in option A. Okay, so the right option is A. Question 15, traffic microsimulation models helps in representing complex traffic systems. So we accept this statement because in traffic microsimulation, we are able to model vehicles at an individual level, right? So there is a lot of complexity that we can pick up by looking at each of these individual vehicles, right? So when we are looking at say macro scale, right, macro simulation, so we are simplifying a lot of these, right? So by considering all the vehicles together, so we are simplifying that, right? So we are not representing the each individual vehicle movements, right? So are there changes, right? So it's a lot simplified when we are looking at the macro scale, whereas in the micro scale, right? So we are able to represent these complex traffic, patterns and the movements, right? So because we are able to model each of them individually, right? So therefore, this is very helpful when we want to represent this complex process. So we accept the given statement. So the right option is A. Okay. So with that, we are concluding today's session. Okay. So yeah, so with that we'll close today's session and then continue our discussions in the next week. Okay. Thank you for it.